So I had to give this talk as a part of APT&M 2020, which was supposed to happen in Oxford. Now it was in online. So I thought I will record this and put this on YouTube. So my talk is titled Imaging Individual Solute Atoms at Crystalline Imperfections in Metals. This work I did at Max Planck Institute for Eisenforschung when I was doing my PhD. So without further ado, let me jump into the talk. So the motivation for my talk stems from any materials engineer's brain. That is, you want to know the material's truth, which is basically knowing the atomic architecture in all three dimensions. And this is especially more relevant for materials which are crystalline because most of the engineering materials are crystalline, especially metals and alloys. And in these metals and alloys, the atomic architecture majorly is governed by defects. Now, there are many types of crystalline defects like dislocations, stacking faults, twins, grain boundaries, interfaces, vacancies, and any material property would be actually governed by how these defects interact with themselves and how they actually interact with any sort of solute elements which you put into your material. Because some solute elements can have a positive interaction with these defects, while some solute elements will have a negative interaction. And sometimes this segregation to these defects can also trigger a phase transformation, which might be something which you engineered, or which could be also something which you did not expect and could be detrimental to the material properties. So understanding this and knowing these things down to the atomic scale, especially in all three spatial dimensions, is very important when we are looking at demanding applications. Because especially in critical applications, knowing these things can matter a lot. For example, nickel-based superalloys, they are used in jet turbine blades in jet engines, and they are usually engineered so that they can survive really high temperatures and high stresses. And this is done so by adding a lot of alloying elements to this nickel-based superalloys, and each alloying element has a certain role to play. For example, titanium and aluminum usually they partition to a gamma prime strengthening phase, and for example, chromium, rhenium, tantalum, they usually partition to the gamma FCC phase, which is the parent phase. Now, one such element, which is rhenium, is added to nickel to improve its creep resistance. Creep is a high temperature deformation mechanism. And in this 1986 paper, it was suggested that rhenium actually forms this short-range ordered solute clusters, and it offers resistance to the movement of dislocations. But it was later suggested in this 2017 paper that actually the most likely mechanism is that rhenium would segregate to the dislocation and forming a quadral atmosphere and offering a solute drag to the movement of dislocations. Now, for a dislocation to break free of this solute atmosphere, it would require higher stress. And if it even breaks free, rhenium would be still mobile enough so that it can catch up and form this solute atmosphere again. So this mechanism was proposed, and we wanted to confirm this experimentally. In order to do that, we took a nickel 2 atom percent rhenium binary model alloy, which was creep deformed at 1050 degrees centigrade to the failure, to almost to the failure. And we got the samples from Erlangen. And to address this phenomena of solute atom segregated to dislocations, we used the most obvious technique which we could imagine, which was atom probe tomography. Now, atom probe tomography is a high electric field technique wherein you have your specimen in shape of a sharp needle, and you field evaporate your atoms so that you can reconstruct them back. Which basically means that atom probe tomography is a time of flight mass spectrometer because it gives you the chemical identity based on time of flights. And since you can reconstruct them back, it is a sub-nanometer spatially resolved projection microscope. So this is well suited to address these problems of addressing segregation to the defects. So we did atom probe tomography on our this binary alloy. However, to our surprise, we did not see segregation. Here, what you are seeing is rhenium first nearest neighbor distribution in the data, which is shown in purple, and it actually matches with the random distribution of rhenium at the same composition. It shows that APT is saying that we do not have any rhenium segregation. So this is very surprising because, as I said in this previous study, there were some mechanical studies which were done and which showed that actually nickel rhenium binary alloy, the same binary alloy, shows improved mechanical properties compared to pure nickel. So this definitely suggests that rhenium should be interacting with these defects in some sense. However, we do not see this from atom probe tomography. So what could be happening? In order to understand this, we did a simulated experiment. So in this simulation, what we did was we took pure nickel and we deformed it uniaxially in a molecular dynamics simulation package. We did so that we can introduce defects into our sample. And once defects are introduced into the sample, we identify these defect volumes using a software called Ovito. And in these defect volumes, we artificially introduce now 15 atom percent of rhenium so that we can simulate this segregation to the defects. And in the nominal bulk composition, which is defect free, we introduce 2 atom percent rhenium randomly to match with the binary alloy composition. So now that we have this deformed volume with rhenium segregated at defects, we cut out a tip from this deformed volume. And to show that actually rhenium segregation is bimodal, we show you a nearest neighbor distribution of rhenium. Here you can see that there is a rhenium segregation peak and there is a bulk random distribution peak inside. So what we do next is use this tip, and using a model called Robin-Roland model, we do field evaporation of this tip. Once we field evaporate this tip simulatedly, we collect this field evaporated events and reconstruct back using the normal atom probe tomography reconstruction algorithms, and we get the reconstructed tip back. Now if we evaluate the amount of rhenium segregated in this reconstructed volume, we see that this bimodal peak is no longer there, and what you see is basically almost a random distribution of rhenium inside. So even though you simulatedly put rhenium into a bimodal distribution state, this rhenium nearest neighborhood should be is being destroyed by the trajectory aberrations because of really high electric field of rhenium evaporation, which basically gives rise to this random distribution of rhenium atoms inside your volume. So in order to actually confirm then experimentally to show that rhenium actually segregates to the defects, we did field ion microscopy. Now field ion microscopy is a predecessor technique to atom probe tomography. And again, similar to atom probe tomography, we usually make a sharp tip out of our crystalline materials. And when we do that, we end up with these features called terraces. This happens because atoms in crystalline materials have to sit at their lattice positions. And since they have to sit at their lattice positions, they cannot form a smooth end form, and you always end up with these terraces pointing along the major crystallographic directions. Now, if you take a small section out of this 3D volume, and if you introduce imaging gas, which is an inert gas, this imaging gas gets attracted towards the tip, which is shown here because of the polarization forces. And once it comes here, it has to get thermally accommodated to the tip's temperature. So it does so by performing a series of hops. And while it's doing this series of hops, because of the high electric field, at some point it will get ionized and it will leave the surface. Once it leaves the surface, it's collected at the detector, and on the detector you are forming a field ion micrograph. Now, the contrast on the field ion micrograph is a consequence of the variation of local electric field on top of each atom. As I said before, since you are forming these terraces, the atom sitting at the edge of the terrace will experience a higher field compared to the atom sitting at the middle of the terrace. So these atoms would be imaged brightly, and this gives rise to the contrast in field ion micrograph. However, the contrast arising because of the chemistry, that is different chemistries of the atoms inside your tip, is still a matter of debate. So at the end, what you get on the screen is a field ion micrograph, and actually some areas you can image all the atoms on the surface. So we did field ion microscopy on our nickel 2 atom per rhenium sample. And straight away, what we saw was that you see an extra half plane in 0 to 2 pole. This extra half plane usually indicates that a dislocation with an edge character has met the surface. And right at the tensile region of this dislocation, you see two bright atoms. These two bright atoms might be rhenium, but we don't know that. And another important feature of this field ion microscopy is that if you are careful with your analysis, you can even image vacancies in your sample. So, to understand whether these brightly imaged atoms are actually rhenium, we wanted to interpret this meaning using DFT, yes, density functional theory. So we took the same terrace 046, which is basically on which we found the dislocation. And on this terrace, drawing parallels with scanning tunneling microscope, wherein you are estimating the tunneling currents on top of the surface of your specimen. And usually this is approximated using an approximation called Tarsal-Hamann approximation. That is, the tunneling current from the tip to your sample in STM is usually approximated to be proportional to the local density of states on your surface. Now, this is similar to our field ion microscopy because you have individual helium atoms which are ionizing from the top of your specimen surface, and they do so by an electron from the helium atom tunneling into the specimen. So if we estimate the tunneling currents here or the ionization probability, we can estimate that based on the local density of states. So we do that, and when we see that we only have pure nickel atoms on the surface, the contrast looks like this. However, if we replace the middle atom with a rhenium atom, the rhenium atom appears much brighter than the surrounding nickel atoms. So these simulations, they actually strongly indicate that these bright atoms could be in fact rhenium atoms. However, the contrast in field ion microscopy can also change because of the local topological changes. So we wanted to confirm this contrast experimentally. In order to do that, what we did was use our LEAF 5000XS, which is our atom probe, which can be switched between field ion microscopy mode and atom probe tomography mode in the same instrument. So when you are doing field ion microscopy, you are at a best imaging voltage and you are in the presence of an imaging gas. So on the screen, you record a field ion micrograph. And since you are not pulsing your voltage, because it's a DC voltage, you cannot record any time of flight mass spectra, which means that you do not get any mass spectrum itself. However, a hypothetical mass spectra would look something like that, with no peaks corresponding to the elements. Now, when you are doing atom probe tomography, you are under ultra high vacuum conditions and you are fluctuating your voltage around the evaporation voltage of your specimen itself. So, on the detector, what you collect are field evaporated surface atoms from your tip, and since you are pulsing, you can also get a mass spectra which shows peaks corresponding to the elements which were evaporated. Now, what we did in this case is to combine both of these. That is, we did atom probe tomography in presence of imaging gas, and we fluctuate from our best imaging voltage to the evaporation voltage of the material itself. So on the screen, since you have an imaging gas and you are near the best imaging voltage, you can obtain field ion micrograph again. However, since now you are pulsing, you can obtain actually a mass spectra. But because of the imaging gas, you have a huge background and you do not see any clear indication of peaks. However, all is not lost, because from the physics of field ionization, we know that when we introduce an imaging gas, the imaging gas will also form an adsorbed layer on your specimen. And now if you trigger field evaporation, that is the removal of surface atom itself, the surface atom, when it is getting field evaporated, it will also induce the field desorption of this adsorbed gas atom, which means that this surface atom and this desorbed gas atom would be spatially and temporally correlated on your detector when you detect them. So if we look for our mass spectra for those events which are actually spatially and temporally correlated, we can filter our mass spectra and we see that you can identify the clear peaks now. This technique, we call it as analytical FIM, because you are rendering analytical capabilities to field ion microscopy. So we did analytical FIM on nickel 2 atom percent rhenium. And when we apply this filtering algorithm to our mass spectra, you can clearly see the rhenium peaks and nickel peaks. And not only that, now you can overlay this information onto the field ion micrographs which you are obtaining. So the chemical information from the mass spectra can be simultaneously projected onto the field ion micrograph which you are collecting on the detector. So when we do so, you see that the brightly imaged atoms are often correlated with the rhenium signal itself. So based on the DFT indications that brightly imaged atoms are rhenium, and from the experimental confirmation that the brightly imaged atoms are rhenium, we took a series of 3D field ion micrographs on the same material, and on a 024 pole which was intersected by a dislocation, we reconstructed it in 3 dimensions, and we can evaluate the number of rhenium atoms and nickel atoms in this defect volume. And when we do so, we measure that there is a 7.5 atom percent of rhenium segregation on these dislocations. And not only that, we can actually reconstruct a 204 type of pole which is not intersected by a dislocation, which allows us to image every atom and do this sort of atomic reconstruction. And here we actually image vacancies. Now the interesting thing is that we see that these vacancies have an associated rhenium atom, whether in first or second nearest neighbor shell. This is interesting because in a 2014 DFT study, it was suggested that rhenium, tantalum, and some other solute elements can have positive interaction, that is positive binding with a vacancy in nickel. And this is really helpful because this can also help improve the creep properties when solute atoms bind the vacancies. However, the statistics in terms of the number of vacancies is a bit limited, and we are further evaluating these materials. So with that, I hope I was able to convince you that we can study this defect and solute interactions down to the atomic scale. And not only that, further what we did was actually to directly input this information into simulations to rationalize why rhenium actually segregates to the tensile side of the dislocation. And if you see here from the bond order potential calculations, we see that when we have rhenium at the tensile region, you have a really good binding when compared to the bulk, whereas when you have the rhenium at the compressive region of your dislocation, the binding is very poor of rhenium atom. So rhenium prefers to be in the tensile region. So this is one consequence, that you could actually input the atomic information which you got from experiments into the simulations to understand why you have this behavior. Now in terms of vacancies, we are further evaluating this with respect to nickel tantalum and nickel tungsten binary alloys, wherein we are trying to get more statistics on vacancy and solute interactions. And The data processing algorithms which I showed you are actually very preliminary, and they can be refined further and optimized further, because contrary to the traditional experimental variables which you have in atom probe tomography, now you have additional parameters such as gas composition, that is the imaging gas composition, imaging gas pressure, which you introduce. And this renders the problem to a multi-dimensional problem, which means that once you optimize all of them, you can have a really good data quality itself. So all this is being carried on at the group of Baptiste Colt at Max Planck Institute for Eisenforschung. And all this is being done so that we can understand this material truth, because the truth is out there. And with that, I would like to thank you for your attention. I would like to thank all the people who are involved in this work and the funding agencies which actually supported this work. Thank you.